Okay, so the topic for our support class today is going to be really brief. The assignment is actually very short as well. We're really just focusing on one topic, and it's dealing with computing the altitudes of triangles, non-right triangles, given some information about that triangle, and then using that to determine whether or not a triangle with the given measurements can exist in the first place. If you've already watched through the 10.1 videos that I put up yesterday for the parent class, you've seen this before. And what we're really looking at is solving non-right triangles in the ambiguous case. That's the SSA case. But if you haven't watched those yet, I'll talk about that here as well, just so you have some context. So to start with, in Chapter 10, the first couple of sections, we're going to be dealing with oblique triangles. Those are triangles that are not necessarily right triangles. We have some naming conventions that are kind of important here. So as we've seen before, the angles in any triangle, we're going to be using alpha, beta, and gamma to represent those. It's Greek. And then the sides are going to have lowercase a, b, and c. And alpha, beta, and gamma are like the letters A, B, and C in Greek. And you'll see alpha will be opposite side A. So letters that correspond to the same thing in different alphabets, Greek and English, will be opposites. Alpha is opposite A, beta is opposite B, gamma is opposite C. I've also labeled this length here H. That's the altitude or height of this triangle, and that's kind of what we're focusing on in the support class today is H. So what we're looking for, or what we're dealing with specifically here, is something called an SSA case for an oblique triangle. And what that means is that we're given information about two sides in an angle where the angle is not an included angle. So to begin with, we're going to be looking at examples where we're given A, B, and angle alpha. We're not shown a picture of the triangle, we're just given the values of A, B, and alpha. The angle that's included between the two sides, we call the included angle, or the included angle between A and B would be angle gamma. It's the angle that sort of joins these two sides together. In the SSA case, as we read this thing counterclockwise, we encounter a side, followed by a side, followed by the angle, which means the angle would not be the included angle here. In those cases, that's where we use this technique that we're going to talk about. So what we're going to be doing is finding out a way to use the information that we're given to do two things. One, compute H, so determine the height of the triangle, and then use it with comparison to one of the measurements that we're given to determine if the triangle that we're looking at is a possible triangle or an impossible triangle. And I'll go into more depth on what I mean by that. But let's start with figuring out how to compute H from this. If we know alpha and B, then H goes together with this side and this angle to form some measurements in a right triangle. This value H, the altitude, creates a right triangle right here. And notice if I were to take the sine of alpha in the context of this right triangle, that's opposite over hypotenuse, which I could write as H over B, or solving for H is equal to B sine of alpha, okay? Now it's important, and we're going to see this in one of the examples that we do, to recognize that the choice of A, B, and alpha are somewhat arbitrary. There's other cases of an SSA triangle. I can have like a B, a C, and a gamma, for example. That's an SSA. The key is that we'll know two of our sides, and the one angle that we know is going to be opposite one of the sides that we know. So we're going to have an alpha and an A, or we'll have a beta and a B, or we'll have a gamma and a C. H is always going to be sine of the one angle that we're given times the side that's not opposite that angle. So if we're not working with A, B, and alpha, we have to rethink that for whatever we are given. Okay, so here's where we're using this. This is a case of an impossible triangle. Let's suppose that we're given information about alpha, B, and A. I know that alpha and b are used to compute the length of h. Now, if I've done that, if I've plugged alpha and b into this up here and determined what h is equal to, what I can do is compare that to the side A that I'm given. The relevance of this side h is it gives me the smallest possible value that A can equal if this thing is going to be a true triangle. And the reason for that is if you look at where A is, A has one, A starts at this upper vertex up here of this triangle, and we have to get it to reach the base of this triangle to complete it, to make a full triangle. Now, the shortest distance from this vertex to this base would be h. That's a straight line downwards, perpendicular to that base. A can be no shorter than h, because if it's any shorter than h, it's not going to reach the bottom. There's going to be a gap here, and that's the key. So in a case like this, if A is less than h, the triangle doesn't exist. But if A is greater than h, greater than or equal to, because it could equal h, then the triangle does exist. That's our test. Okay, so let's do a couple of examples really quickly here where we want to determine the height or altitude of a given triangle, and then determine whether the triangle can exist in the first place. So as before, I'm given information about A, B, and alpha. The first thing I want to do is compute h. So we saw that h was equal to b sine of alpha. That's 12 times sine of 50 degrees. Okay, that goes into a calculator, and for this we're going to get something approximately equal to 9.19. Okay, this represents the smallest possible value that A can be if this is going to be a triangle. Notice that A is bigger than that. That's a good thing, because that means that this could be a triangle. So I would say A is greater than h, so this triangle exists. Okay? That's all there is to it. Let's try another one. In this case, notice it's not A, B, and alpha that I'm given. I'm given B, C, and beta. Okay? So even though it's not A, B, and alpha, this is still a side-side angle, or SSA case. So we can apply this approach. Just to start with, I want to find h. And even though the formula that I came up with before said that h is equal to b sine of alpha, that was dependent on knowing A, B, and alpha. But like I said previously, we adjust and we just look at whatever angle we are given, sine of beta, and then we multiply by whichever side is not opposite beta. I know that B, side B, would be opposite angle beta, so I actually should be multiplying by C. That's going to look like 25 sine of 80 degrees. And again, that goes into a calculator. This one comes out to approximately 24.6. Okay, now when I compare that, I want to compare this to the one remaining side, which is B. I haven't used B yet. Okay, and again, we're comparing, this was compared to A in the previous example, but in general, we compare it to whatever side is opposite the angle that we're given. So B in this case. This is a lot larger than B. So I would say in this case, B is less than H. But if this triangle was supposed to exist, then B would have to be at least as big as H, which it's not. So I would say, so this triangle does not exist. Okay? Fairly straightforward. Notice these problems go really quick, and the assignment that I'm giving you for this only has 6 problems, but this is how you're doing them. Compute H, and then compare it to whichever side is opposite your given angle, and make a determination whether or not that triangle exists, and then write a little sentence explaining that. Pretty straightforward. but this will come in handy when you are working through 10.1 and trying to determine what case you're looking at for SSA triangles.